All right, it is 2:01, so we'll get going. This is Rick Nelson, U.S. Fish and Wildlife Service in Bismarck. And good afternoon, everybody, and welcome to the March edition of the Plains and Prairie Pothole Science webinar. We're scheduled for an hour today, and we will expect to have some time at the end for questions and hope that folks will avail themselves of the opportunity to ask either over the phone or by raising your question through the chat box. And we'll get to those questions at the end of our webinar. We are recording this webinar today, and it will be posted on our website within a day or two after completion, so you can check it out there and share it with folks who may have wished to attend but couldn't make it for some reason. I would remind everyone to please put your phone on mute so that we minimize the background noise during the presentations. And with that introduction, I will introduce our guest speaker today. It's my great pleasure to welcome Brian Tangen to our webinar series. Brian's an ecologist with USGS Northern Prairie Wildlife Research Center. He focuses his research on wetland ecology with emphasis on the Prairie Pothole region. And Brian has studied a wide range of topics along the lines of wetland ecology, including aquatic inverts, ecosystem services assessment, carbon and greenhouse gas fluxes, hydrology, soils, vegetation. He's kind of covered the gamut of everything, and today he's going to be talking to us about subsurface drainage systems. So with that, it's my great pleasure to turn this over to Brian, and Brian, you may begin at any time.
All right, thanks, Rick. So as Rick mentioned there, we have a tendency to delve into a lot of topics, and I claim to be an expert at none of them, but I have enough of a familiarity with a lot of topics to be dangerous, I guess. So today I'll be talking about a recent study that we completed examining the efficacy of drainage setbacks for limiting effects to wetlands, or more specific to wetland hydrology in the Prairie Pothole region. I guess we usually have a lag here, so I'll try to give a second between slides. Let's start off, acknowledge a few of the partners and folks involved with the study. First of all, I'd like to thank the Plains and Prairie Potholes, LCC, U.S. Fish and Wildlife Service, the Chase Lake National Wildlife Refuge was instrumental in helping with this project. And then from the Northern Prairie Wildlife Research Center, had Ray Finachero, Charlie Dahl. They've since moved on to greener pastures, but they did all the heavy lifting for this study, as well as Jacob Meyer and a lot of the other field crew. So I just wanted to acknowledge all of them before we get going. Okay, so this presentation is essentially based on a recent publication that came out in the Journal of Fish and Wildlife Management by Ray Finich and myself. And just as a note, since the publication is out there, I'm not going to bore everybody with a lot of nuts and bolts and nitty-gritty details of the methods and stuff, but they can all be found in the publication. Although if there is any specific questions, feel free to ask. So a couple of main objectives of this research were to provide sort of an initial assessment of prescribed setback distances for limiting effects to wetland hydrology, and also to assess the potential effects of reduced precipitation runoff on wetland surface water characteristics, primarily looking at the wetland ponded surface area in this study. That resulted from, resulted from subsurface drainage effects. So just as a little overview here about what I'll be talking about today. During the initiation of this project, back in roughly 2012 or just prior to there, and as the project progressed, it became fairly evident that there was a lot of ambiguity pertaining to various terms and concepts related to wetlands and associated effects of drainage. Thus, in the manuscript, we included a significant amount of information in the introductory material in an attempt to introduce, define, and clarify various terms and concepts. So likewise, I'll begin this talk by providing an overview of various terms and concepts that we use in the manuscript and that I'll use throughout this talk. After that, I'll move on to a little bit of the study background, design, results, overall conclusions, those sorts of things. And then at the end, I'll highlight a few related studies and discuss some potential research topics moving forward. So starting out here with a few of the common terms I'll use throughout the presentation. First one is subsurface drainage systems. These simply refer to, in the case that we're talking about, perforated plastic drainage pipe that's installed below the soil surface in various configurations. You can see, field-wide pattern tile draining, or you can target local areas. This is also referred to as tile, based on the old clay tiles that these evolved from, so I'll probably use those terms interchangeably as I'm talking. The second term that I'll introduce here is a setback, and this basically refers to a protective buffer or distance between a wetland and a subsurface drainage system. It's also known as the lateral effect distance of the tile, basically a distance on either side of a tile that the tile affects in terms of removing or affecting soil water. And then throughout, when I'm referring to a wetland catchment, I'm referring to sort of the wetland basin proper, as well as the adjacent uplands and contributing areas, sort of the entire wetland system, I guess you'd say. Okay, so I'll start out with kind of showing a depiction of a lateral effect distance, or the setback that we'll be referring to. So these setbacks are calculated using scope and effect equations, along with site-specific soil and subsurface drainage system characteristics, such as, depth of the system, size of the drainage pipe in terms of diameter, and those sorts of things. And essentially, the lateral effect distance represents the distance on either side of the tile line that is affected by the tile in terms of capturing or removing water from the soil profile. In the photos I'm showing here on the left, you see an aerial photo. Oh, is that my phone? Everybody else hearing that? Okay, sorry. So anyways, on the photo on the left shows relatively evenly spaced tile lines in a field. This is kind of referred to as pattern tiling. And this sort of demonstrates the intended use of these lateral effect distances, showing they're basically used to optimize the spacing of the tile lines in a field. And the diagram on the right shows the lateral effect distance or setback in relation to a wetland. So you see you have, a wetland basin, a setback between the wetland basin and the tile. And essentially, in a relatively flat terrain, the setback should place the wetland outside of the lateral effect distance of the tile. So the goal would be to limit any effects to the hydrology of that wetland. However, wetland surface water often it's not necessarily isolated to the basin. Instead, there are connections to the near-surface groundwater as well as saturated soils adjacent to the wetland. Thus, there could be, an effect to the wetland hydrology even in a situation as this where you're using a setback even in a relatively flat terrain such as this. Additionally, there could be, other effects that I'll sort of run through here in some subsequent slides. I guess I'd like to start out here, provide a brief overview of the primary components of the wetland water balance and sort of discuss the potential effects of a subsurface drainage system. So the primary inputs to prairie pothole wetlands generally are, runoff from snowmelt, direct precipitation to the, ponded portion of a wetland, and then precipitation runoff, both surface and near-surface runoff from the surrounding catchment. And I'd like to emphasize, too, that this near-surface runoff can be, fairly significant, and we don't really differentiate between surface and near surface. We just kind of lump it all together. Primary losses are attributed to evapotranspiration, infiltration, and in some cases surface outflows if a wetland fills past capacity. And depending on the wetland's location in the landscape, groundwater interactions also can play a role in the water balance. In terms of potential effects of subsurface drainage systems, there's important factors and considerations that include the relation to the groundwater, whether it's a groundwater, recharge, discharge, or flow-through site. In terms of generation of precipitation runoff, important factors include, precipitation intensity and duration, antecedent soil moisture conditions, catchment slope characteristics, vegetation characteristics. All those will, affect the water balance, and thus are sort of interrelated to any potential effects of subsurface drainage systems. So in subsequent slides, I'll discuss various ways that the subsurface drainage systems can affect wetland hydrology. First, I'll go through a few last terms and concepts here. So oftentimes in wetland drainage is thought of as a system that directly removes the water from a wetland, resulting in effectively drained wetland basin. Or this picture on the right is an example of a drained wetland where you'd have a riser pipe coming up in the middle and the water is essentially directly drained. However, subsurface drainage systems can result in intermediate or indirect drainage as well. So here we list a few of the general types of drainage that we often refer to. So like I said, we have your direct drainage. You're going to have drainage tile could go, through or beneath a wetland, and you may have, like I say, the riser pipes. So you're essentially directly draining a wetland, and they're typically highly effective. You can also have the adjacent drainage, where the subsurface drainage system is placed adjacent to the wetland, but generally outside of the wetland and boundary. This could include, like encirclement is a term you'll hear, where the tile would essentially encircle a wetland. And in these sorts of situations, generally in flat terrain, you can not only affect the soil pore water and any groundwater that could be feeding that wetland, so the effects could be quite variable there. And then indirect drainage, which is generally the focus of this study, is the interception of surface runoff from the catchment surrounding a wetland. And this is a more important concept in more high relief terrains where you're going to have little higher gradient slopes. So another important concept with all these types of drainage is topography, or sort of the landscape. So here's an example of drainage in a relatively low relief terrain where the subsurface drainage system has the potential to affect the wetland via the lateral effect. This is similar to the earlier example that I showed. So the example on the right here shows the placement of tile using a setback. The example on the left shows the placement of a tile, an example of it anyway, without a setback. So in this situation, the subsurface drainage system has the potential to affect things such as the soil pore water, wetland surface water, near surface groundwater, et cetera. And that would all depend on factors such as the setback distance, the groundwater connection, soil properties, characteristics of the drainage system, and those sorts of things. So there's a lot of factors to consider. It's not real simple and straightforward. So here's a similar example showing the indirect drainage that sort of can affect the surface runoff. And you'll see this in a higher relief terrain where the subsurface drainage system has the potential to affect the wetland by essentially intercepting the surface runoff or interrupting it. So in this case, on the left and right, you'll see, similar to the previous slide, a setback with drainage with and without a setback. And in these cases, the effective area of the tile is essentially above where the tile is placed or upslope of it. So basically, if you're on a slope, the tile is even the ground, it would have the potential to intercept precipitation coming downslope to the tile. And similar to the previous slide, the important factors to consider here would be, the catchment slope and soil properties and the characteristics of the drainage system and those sorts of things. So I think I've covered most of the terms and concepts here that I wanted, at least so it'll be clear, I think, what I'm talking about through the rest of the talk. And now I'll sort of transition from these terms and actually get into the meat of the study. So a little bit of the history of drainage. So the use of artificial drainage systems, both surface drains and subsurface systems, to decrease soil water content or drain wetlands, basically with the purpose of enhancing agricultural production or urban development. It's been a common practice throughout the history of the United States. Traditionally, the purpose of agricultural drainage has been to, lower the water table of poorly drained soils with the goal of improving soil aeration and crop production. Just kind of threw in here a little picture I swiped from Johnson et al. Publication showing an early 20th century ditching machine. They've come a long way since then, but it's kind of a neat picture. So in the Prairie Pothole Region, historically, subsurface drainage systems have been pervasive in the eastern portions of the region, basically in Iowa and Minnesota, sort of depicted by the red circle on the left here. Most of the wetlands in this area have been drained for a long time, and there's not a lot of natural wetlands remaining. Recently, the use of subsurface drainage systems has expanded, rather rapidly into the eastern Dakotas, sort of highlighted by the yellow area here on the right. And this is mainly owing to high commodity demand. Basically when corn prices started skyrocketing, that's when drainage really started to take off. And the subsurface drainage systems, they primarily started heading out into the relatively flat areas of the pothole region there in the eastern Dakotas, but they did also start expanding into the other areas as well. So here I just wanted to provide a few snapshots for those that aren't familiar with it. What does subsurface drainage or tile look like? I just threw up a bunch of pictures here. In the upper left-hand corner, you can see you get these large rolls of plastic tile you see out in the field. Those are what go in under the ground. Occasionally you'll see the outlet pipes for the system. It could be into other wetlands or into drainage ditches, wherever they can find a good spot for it. See a tile plow in the lower left. That's how they typically install the systems. Then the other pictures are just various aerial shots of different sort of layouts in the field. You see some pattern tiling where essentially the whole field's covered, and you'll see some targeted draining where you can see them, targeting wet spots or little wetlands in the fields. So essentially that's what tile looks like in a number of scenarios. So here I'll touch briefly on common guidelines and regulations. So where regulations apply, which should typically be for a landowner participating in farm bill programs, you'd be required to use setbacks when installing subsurface drainage systems around a wetlands. The setbacks are prescribed generally by the Natural Resources Conservation Service. They're calculated using various scope and effect equations, and the rules and guidelines, vary by state and sometimes within states. As I mentioned earlier, they're originally designed to determine the optimal spacing for tile lines, but they are also used to limit effects to wetlands by providing that buffer between the system and the wetland. However, they've really not been well vetted for this purpose, which is one of the reasons that this project got started. So basically, the project was initiated, based on a lot of discussions with various U.S. Fish and Wildlife Service personnel in the region. The service oversees a large, amount of fee and title lands in the Dakotas, and basically began receiving, increased requests to draining catchments of protected wetlands, sort of like wetland easements. These lands, as I say, they include wetland easements. They contractually stipulate no draining, typically referred to, as direct draining. But as we discussed earlier here, subsurface drainage systems in the catchment could represent a form of indirect drainage that could affect wetland hydrology. So basically, to protect, these easement wetlands, potential drainage policies could range from, no drainage in the catchment to drainage using setbacks or, somewhere in between there. And so this research need was to assess, basically the efficacy of setbacks for protecting wetlands, and it was aimed at providing sort of an initial assessment of the efficacy of setbacks for limiting potential effects to wetlands. And basically, these results were meant to inform management and policy development and generate sort of some thoughts and discussions along the way. So the overall objectives of the study, first we wanted to dissect the wetland water balance, basically look at the inputs, see sort of what the relative contributions from those different sources were. We wanted to provide an initial assessment of the setback distances for limiting effects to wetland hydrology. And we wanted to assess the potential effects of reduced precipitation runoff on wetland surface water characteristics that result from subsurface drainage. And the study had both, a field and a modeling component. So a quick run through the field study design here. We're mainly focused on 4 wetland catchments. We monitored them and worked on them roughly from 2012 to 2015. In 2013, we had subsurface drainage systems were installed in 2 of the catchments using site-specific setbacks. And as a note, these were isolated systems. They weren't throughout the field. They were isolated within the wetland catchment, and this allowed us to sort of assess how much water these systems could potentially be removing from the catchment without having to try to parse it out from the entire field. And in this field, we monitored water levels of the wetlands, weather components, precipitation, those sorts of things to help calculate and parse out the water balance of the wetlands. Conducted some detailed topographic surveys to help with some of the modeling efforts. And we also monitored the discharge from the subsurface drainage systems. I guess as a note, these systems were located just north of Jamestown, and there's some variation, but they're fairly similar in size and soils and all those sorts of things. So as I mentioned, in some of the previous slides, the effects of a subsurface drainage system will vary according to a lot of factors such as terrain and relative location of the system, etc. The effects of direct drainage and lateral effect drainage and sort of the low relief terrains are fairly straightforward. Thus, for this study, we were primarily interested in potential effects of a high relief terrain, specifically what could the effects be on the generation of surface runoff and inputs to the wetland. So the first step of our study was to assess the primary components of the catchment water balances. We did this using a mass balance approach, where we calculated the volume of direct precipitation to the ponded portion of the wetland and calculated the volume of precipitation runoff simply by subtracting the precipitation volume from the total positive change volume of the wetlands. This gives us a pretty good handle on how much is coming in from surface and near surface runoff. We also calculated the volume of snowmelt runoff, at least for 2014 and 2015. Those are the only years we had the sufficient data to do so. And basically, the overall goal is to assess the potential for subsurface drainage systems to affect wetland hydrology through disrupting runoff. So a little bit of the results of that initial step. Results of the water balance suggested that runoff can be a significant contributor to the seasonal water balance of pothole wetlands. These graphs basically show for the 4 wetland catchments by year the volumes attributed to precipitation runoff, direct precipitation, and snowmelt. At least for the 2014 and 2015, we did not have snowmelt for 2013. And basically, you see, variation depending on, wetland and year combinations, as you would expect. But in general, you can see that precipitation runoff accounted from anywhere from 20 to 50% of the seasonal water balance of a wetland. So there is significant potential there to be affected by a subsurface drainage system placed in the catchment. So after that, our second step was to assess the drainage discharge volumes from our localized subsurface drainage systems, see how much water is being removed from the catchment, and with the relevance being that the portion of the water that could contribute to the wetland via surface runoff and near surface runoff would be going out into the tile. So to do this, we measured flow rate and volume using a flume setup, at the tile outlets. And in general, overall discharge from the system was characterized by intermittent and trickle flows. The volumes were relatively small, as really would be expected from the placement in the catchment. We used setbacks, so the tile was placed, generally away from the wetlands pretty good. And essentially the area above the tile or upslope of the tile was relatively small. Here's sort of a figure that shows the affected area of the tile. Sort of the dashed yellow lines are an approximation of the wetland catchments. The red lines are an approximation of some of the tile lines. So as you see, the setbacks result in the tile being placed well upslope of the wetlands, and there wasn't a lot of area upslope of the tile lines to be intercepting precipitation, runoff, and poor water. So that, and that makes sense looking at the catchments, and then it also is reflected in those small water volumes that we captured coming out the tile outlets. Here's a example of the similar slides from earlier, the water volumes attributed to the different sources of water. And then on this one, we added the tile discharge on top in red. As you can see, relative to the snow melt, precipitation, runoff, the discharge volumes are quite small. And, as a note, too, only really a portion of that discharge, if it's coming from the catchment, would likely have the possibility to contribute to the wetland due to the proximity and infiltration and those sorts of things. So based on this, the water removed by the subsurface drainage systems likely would not have a noticeable effect on the catchments. Okay, so as a quick recap of the first two portions here, we looked at runoff, found that it can be an important component of the seasonal water balance of these wetland catchments, and the discharge volumes from our localized subsurface drainage systems that were installed with setbacks were minimal. Okay, so the third step of the project was to assess the potential effects of subsurface drainage systems to wetland surface water characteristics. Namely, we were looking at ponded wetland surface area as an indicator. Essentially, if tiles placed in various configurations around a wetland, what would the potential effects be? So our approach to this was to develop a simple wetland hydrology model to simulate surface water expression, specifically the ponded wetland surface area. Here, the image on the right shows the model results along with observed results from the water level monitoring for each of the wetland and year combinations. And I know here you probably can't differentiate the lines much, but essentially the models performed well and reflected the observed conditions. This model, we then used the model to assess the potential effects through some simulations. We also examined model performance, sort of the way to test for the potential effects of subsurface drainage systems. We modeled the potential effects specifically of reduced precipitation input runoffs, or runoff to the catchment. So what would the wetland the wetland surface water expression be if a portion of the surface runoff was taken away via tile. So the model is presented in detail along with the manuscripts. I won't go into it too much here. Just give you a brief overview. It's basically a model that can help support assessments and do some scenario modeling. It's a simple water balance model that basically considers the ice-free season, considers the primary factors of the water balance that we discussed earlier, and the outputs include sort of ecologically relevant variables such as depth, hydro period, and surface area. So to begin with, we conducted a simple analysis to assess and compare model performance, basically comparing modeled versus observed ponded surface areas. Sort of the rationale of this simple comparison was that if models consistently over-predicted pond and surface area, basically are they over-predicting inputs for the post-drainage sites, the years after the drainage systems were installed, compared to the pre-drainage and non-drain sites, that this would indicate, a potential effect of subsurface drainage systems that could be explored further. Overall, the models did not consistently over-predict ponded surface area. So basically results or model performance vary depending on, site year combinations, essentially demonstrating expected variability. Based on this initial examination, any subsurface drainage system effects were minor relative to the accuracy of these models. And, alone this assessment wouldn't support any strong conclusions or anything, but it's just another piece of the puzzle when combined with the subsequent results. So next we use the model to simulate effects of subsurface drainage systems to wetland hydrology based on a reduction in precipitation runoff. The potential effects really can be complex and variable due to a lot of the factors that we discussed earlier, the soils, precipitation intensity, the subsurface drainage system and catchment characteristics, all those sorts of things. And it would really be difficult to employ a super complicated model to try to model each of those possible effects. There would be a lot of high uncertainty, I guess. So we employed our simple water balance model using some simple general scenarios. Basically, we modeled the hydrology based on the subsurface drainage system installed with setbacks and without setbacks. And due to the uncertainty of the actual effects of the drainage system, we modeled sort of the best and worst case scenarios. We have the baseline, which would be a 0% reduction, and then for the simulations where we're simulating a tile system, we assume that the systems reduced or result in a 100% reduction in runoff inputs from above or upslope of the tile. Just kind of give you a visual representation of these scenarios. On the left is basically a figure showing a wetland catchment that includes a subsurface drainage system, which would be the big black line. The gray shaded area is the area upslope of the drainage system, and this area represents the potential affected area where precipitation runoff could be intercepted by the tile, or the runoff from that area could be accepted by the tile. And on the right, there's a depiction of our two model scenarios. So in this figure on the right, the catchment on the left shows a subsurface drainage system installed without a setback. So essentially the entire upland zone of the catchment, which is shaded gray, represents the potential affected area. For the same figure on the right, the catchment on the right shows a subsurface drainage system installed with a setback. So only the portion of the upland zone upslope of the drainage system represents this potential affected area. And as I mentioned earlier, for the simulations, 100% of the precipitation runoff was reduced according to this area above the setback distance. So for example, if the site-specific setback distance resulted in 10% of the catchment being upslope or above the tile, the precipitation runoff volumes were simply reduced on a daily time step by that amount, sort of giving that worst-case scenario. So now we'll kind of transition over and go through some of the simulation results where we compare the two scenarios with the baselines. So we compare ponded surface area. Like I said before, it's often used as an ecological meaningful variable. And the model outputs also include depth and hydro period. Those can also be looked at. So these graphs essentially display the ponded surface area for the 4 catchments for the 3 years. There's 3 lines on each of the for each of those combinations that represent the baseline and the 2 model scenarios. Now, I know it's probably difficult to see the details, but the take-home message is that the surface areas of the with setback scenarios, so when the tile was installed with the setback, these areas were slightly reduced compared to the baseline, but they're fairly similar. While the without setback scenarios show a higher reduction in surface areas, to varying degrees depending on precipitation year and catchment and those sorts of things.
Of the upslope and then like a portion between the tile and the wetlands.
So, based on these simulations, the with setback scenarios resulted in roughly a 7% decrease in daily ponded surface area, while the without setback scenarios resulted, in a roughly 24% decrease. The reduction in hydro periods range from a few days to a few weeks, depending on catchment and year. So, overall conclusions from those various components: precipitation runoff was or at least can be an important component of the seasonal water balance that has the potential to be affected by drainage. Drainage with setbacks resulted in minimal discharge from the drainage systems. The model simulation suggested that the drainage systems could affect hydrology, depending on whether setbacks were used or not, along with the catchment-specific factors and characteristics. But in totality, when you put the field data and the model simulations together, it suggests that the setbacks should reduce but possibly not eliminate effects to the water balance of wetlands. And obviously with a sort of a pilot or initial sort of study like this, it is constrained. It's low replication. We're in a high relief terrain. The site-specific catchments and subsurface drainage characteristics and the weather years that we dealt with there. So those are constraints on this initial study. Okay, it looks like I'm going to keep going here if I'm run out of time. But so far, I've kind of focused on, wetland hydrology. But the overarching question is, what are the ecological effects? For example, what would reduced surface areas or hydro periods mean to various species of migratory waterfowl during various times of the year, for example? These type of effects would vary by species, stage of life cycle. But, we're not going to explore it in detail here, but in terms of management decisions, it would have to be made on a case-by-case basis depending on the goals and objectives and species, being managed. Additionally, for this initial assessment, we focused exclusively on our study sites during the time period of study. Additional questions could include cumulative effects over time. For example, if a wetland began the year slightly lower for a number of consecutive years, it would eventually dry or become more seasonal. Also, even if the effects were minimal, what would the cumulative effects be across a landscape? For example, if 10,000 wetlands were reduced by 5 or 10%, what would that mean on the landscape scale? I'll try to run the last few slides quickly so I don't run out of time. But so although subsurface drainage systems and wetlands has been a sort of a hot topic of concern that has generated a lot of discussion in some general non-science articles, there's not really a lot of relevant research, especially in the Prairie Pothole region. So in the following few slides, I'd like to take a couple minutes to highlight some recent relevant research and discuss potential directions of future research. So as a companion study to our field study and modeling study, Ray Funichiro gathered the available information pertaining to drainage tile permit locations in the eastern Dakotas and released them as a USGS data release. These data are available to support various spatial analyses and a lot of lessons learned from that portion of the study. For example, the permitting process or lack thereof in some cases, varied almost at a county-by-county level throughout the Dakotas, and it really makes identifying and assessing tile very difficult at any sort of spatial scale. Another companion study led by myself and Mark Wiltermuth from Northern Prairie identified key catchment and subsurface drainage system characteristics to consider when assessing drainage setback. This effort also assesses the efficacy of setbacks for totally eliminating subsurface drainage systems from the catchment of specific easement wetlands throughout North Dakota. And that currently is a revised manuscript has been submitted to the Journal of Fish and Wildlife Management, and we're awaiting a decision on that one. Another companion study to our field study was a collection of water quality data from both our study wetlands and the associated drainage systems. These samples were analyzed for standard water quality variables as well as a large suite of agrochemicals. These data have also been released as a USGS science-based in the data repository. While these data were limited in scope, results demonstrated sort of typical variability in standard water quality variables such as ionic composition and specific conductance and those sorts of things. And additionally, 7 of the 93 agricultural chemicals were above the reporting limit for at least one sample. And these generally were common agricultural herbicides. And just as a note, these data were part of a larger regional water quality study led by Matt Schwartz of the U.S. Fish and Wildlife Service, and I believe a comprehensive report is forthcoming on that portion of the study. Another related pothole study was conducted by Werner et al., and this was a modeling study examining effects of variable tile placements within the catchment. And then lastly, there's a growing body of work by researchers at the Northern Prairie Wildlife Research Center examining various aspects of consolidation drainage, which is essentially draining small wetlands into larger wetlands. So while there is some ongoing work and there has been a few studies, there's not a lot out there dealing with actual hard science sort of articles in the pothole region. So just a couple notes on future research. We feel that it should encompass a range of landscapes, both high and low relief, a lot of wetland types, those sorts of things. We look at a variety of subsurface drainage system characteristics as far as setbacks and depths of systems and or scope of the system in a catchment. Long-term studies would be ideal, especially combining field data and modeling due to all the inherent variability related to this subject. And then looking at various scales, landscape versus catchment scale, potential downstreams effect in a watershed, and then, of course, more importantly, looking at the ecological effects. And I guess with that, I think I swung in at about the time limit, so that's all I have for there, and I'd be willing to take any questions.
Excellent. Thank you, Brian, very much. Very informative webinar and lots of good stuff coming out of that particular study. So we have about 15 minutes, folks. We'll open it up to questions. Anybody have a question for Brian? Go ahead. We do have one via chat. What model was used to determine the setbacks?
They were actually, it was the Van Schilfgaard, if that's how you say it correctly, model. They were actually, we had the NRCS come out and they calculated the setbacks. And we validated them with there's a setback calculator on the North Dakota NRCS website also, and they're about the same. So they were the Van Schilfgaard model using the site-specific characteristics.
Thank you.
And as a note, too, with the setbacks, we did apply them, from roughly the maximum extent to the wetland. So, it really set them back well in the catchment, whereas, an operator may, on a dry year, you could set them a lot closer than the actual setback, obviously, if you were going to use, like, the water is the edge or something. So that's an important factor to consider, as well as how the edge of the wetland is set when you're applying the setback.
Hey, Brian, this is Rocco Morano from Game Fish and Parks in South Dakota. I just have a quick question. You mentioned that the outputs to the drainage systems basically weren't very high. I mean, do you think that was because of the aspect, and maybe perhaps that the site was relatively well drained upslope, and maybe they really weren't functioning as, you know, on a lower aspect type of a system would work?
Yeah, I think you know that's part of it, and like I said earlier too. I mean, if you were at the site and you looked up there and you just look up and say, yeah, these aren't going to kick out much, because they were up there in the top of the slopes and there really wasn't much area above them. So I think it's probably a combination. Yeah.
Other questions? Fire away, folks. All right, well, hearing no other questions, I want to take this opportunity to once again thank you, Brian, for a great webinar, and thanks everybody for calling today. We have recorded the webinar, and it'll be up on our website in a day or two. So thank you again for participating today, and have a good afternoon, everybody.